Hi, I'm Emil, and I'm excited to present our new work, Rosetta Neurons, Mining the Common Units in a Model Zoo. This is joint work with Yossi Gendelsman, Alyosha Efros, and Asaf Shuk. Let's say we have a classifier classifying this image as a cat. But do we really know what's going on inside? David Bao began to answer this question with this network dissection line of work, where he correlated activations from a pre-trained model with semantic segmentation masks. And he found that neurons can correspond to visual concepts. But this is done for just one model. And today we have a zoo of models trained on different tasks with different architectures and on different data sets. So the question we want to answer is, do these models learn their own unique view of the world, or is there something common in their representations? One way we can go about doing this is leveraging semantic annotations, as David Bao did. But this will only find segment-related neurons, and we know the world is much richer than what a human can label. Thus, we adopt an unsupervised approach. So let's zoom in to just a pair of models. In our method, we leverage a generative model to generate a bunch of images, which are then fed into a discriminative model. We then bank up all the activations and calculate the pairwise similarity across the networks to find the best matches. But some of the matches can be noisy, so we take the mutual nearest neighbors and only keep those. Now, if we zoom out, we'll repeat this process for multiple pairs of models grounded in the same generative model. Then we only keep those neurons which match with the same set of generative neurons. And what we find is, given an image, these neurons will fire for the similar visual concepts. We call these the Rosetta Neurons because the Rosetta Stone was an ancient artifact which translated between different languages. In our case, the Rosetta Neurons translate between the different languages of these different models. And what we find is that there are around 100 Rosetta Neurons, which is around less than 1% of the neurons in a single model. Here are what some of these Rosetta Neurons can look like. I'd like to point your attention to number 3, which appears to be the contour of an object, which is something that a human would not instinctually label for a semantic segmentation task. Or number 4, which is contact with the ground. The Rosetta neurons can also be leveraged for generative tasks, such as GAN inversion. If we want to invert this image into the latent space of a GAN, we'll optimize Z with a pre-trained GAN to best match the pixels of this image. But what we can actually do with the Rosetta neurons is we can feed this image through a discriminative model such as Dino, and then optimize the latent of the GAN to best match the activations coming from the Rosetta neurons. What this allows us to do is sort of translate from a Dino language to a GAN language. And what we end up with is a projection of the image into the distribution of the GAN. Here are some other examples of what these translations can look like. And to the left are examples of what the activations we match are. The Rosetta neurons can also be used for spatial edits. Given a set of Rosetta neuron activations, we can apply a geometric transformation and then optimize the latence of the GAN to best match those activations. Or we can target a specific neuron for fine-grained edits. In summary, we show the existence of common neurons across multiple networks trained on different tasks with different architectures and on different data sets. And we do this in an unsupervised fashion. Additionally, because we leverage a generative model in our analysis, we can use the Rosetta neurons for a variety of generative tasks in image inversion and editing. Thank you.